Hello everyone, welcome to Thermofluids Lab. Today we're going to be talking about Rankine cycle. Rankine cycle is basically the thermodynamic cycle that is used for power generation involving steam. It was first introduced by William John Rankine, a Scottish engineer back in 1883. So the major components of a Rankine cycle is basically you have a pump, a boiler, a turbine, and a condenser. Come to think about it, basically a steam power plant cycle. The various usage of Rankine cycles can be found out all throughout power industry. They're used in coal power plants, natural gas, nuclear power plants, even in concentrated solar power plants. They're also used as combined gas turbine and steam cycle power plants. There are other types of Rankine cycles. They're called organic Rankine cycles because on this type of Rankine cycles, the working fluid that is used is, instead of water, some kind of organic compound. So these kind of Rankine cycles are usually used for waste heat recovery, biomass power plants, geothermal power plants, solar power plants. So basically where you have very low amount of heat input needed to evaporate your working fluid, those kind of power plants that use organic working fluids and work on organic Rankine cycle. To understand the Rankine cycle, we must first know the laws of thermodynamics. The first law of thermodynamics talks about conservation of energy. It says that energy can neither be created nor be destroyed and can only be transferred from one form to another. Think about the picture on the right. You have some system at state 1. At any given time, it has an internal energy E. Now, if you want to get the system to the state 2, it can only be done by either addition of heat or by removal of heat from the system, or by doing some work to the surrounding environment, or by adding work to the system. So the only way you can move from state 1 to state 2 is either by heat transfer between the systems or by changing work done by the system between the states. Now when you reach to state 2, you will have a different internal energy, that is E2. The first law of thermodynamics states that the change in the internal energy between the states of system is equal to the heat transfer or heat added or removed from the system plus the change in work done by the system or to the system. Now look at the picture on the bottom. So if you're following the first law of thermodynamics, you can see you have a state of high temperature, TH, and a state of low temperature, TC. Now, heat moves from higher to lower temperature. So, heat would flow from TH to TC throughout the system from state 1 to state 2. Now, during this time, you would have some work done by the system due to this flow of heat. Rankine cycle basically works on this principle, using high temperature fluid and extracting that heat to produce energy or work done. Now, the second law of thermodynamics talks about entropy. It states that the entropy of an isolated system always increases. Now, to understand this, think of a clean room. If you go and start staying on that room, no matter how well or how tidy you keep the room, it will always get a little bit messier and disorderly over time. Now, you can try to get it back to its original state, but then you'd have to put a lot of effort to cleaning it. Now, think about entropy this way, that no matter what you do, the room doesn't get back to its original state, so entropy has increased. So this is called irreversibility of a system. So if you think about a Rankine cycle would have irreversibilities. Suppose in pumps, in boilers, in compressors, in turbines. So no matter what you do, you'd have, say, in turbines, frictional losses. In pump, frictional losses. You'd have pressure drop due to friction. These things you cannot get back. So the energy used up in friction is lost by frictional heat or some other way. So this process becomes irreversible. So that means the entropy has increased. Now, according to this increase of entropy or irreversibility phenomena, the second law of thermodynamics basically says that a 100% efficient system is not possible. Let's talk about the ideal Rankine cycle. An ideal Rankine cycle would have a pump, a boiler, a turbine, and a condenser. You'd add heat into the boiler, make steam, and use that steam to rotate a turbine and generate electricity, and the exhaust from the turbine or steam from the turbine would be fed through a condenser to condense it back to its liquid form, and then water would be pumped in again to feed to the boiler and keep on going with the cycle. Now, the process of the Rankine cycle is shown in a temperature versus entropy diagram on the right. Now, on the TS diagram, the process 1 to 2 is isentropic compression of the water. That is basically the work done in the pump. The 2 to 8 point is isobaric heat addition. It is basically 2 to 3. The whole point is isobaric heat addition. Now 2 to A is where you have the water temperature increasing but no phase changes occurring. So 2 to A, you have heat addition but no phase change. A to all the way 3, you'd have first an isothermal phase changing phenomena where water would change to steam, and then once it becomes steam, the heat is added and it becomes superheated steam and gets to point 3 where temperature would increase again. Now 3 to 4 is isentropic expansion in the turbine, and this is where the turbine work is done, and you would have drop in pressure and temperature. And 4 to 1 is the isobaric heat rejection in a condenser. Basically, this is where the cooling tower is used. And then you again go to 1 to 2. You use that water again to get the steam, get to the boiler with isentropic compression. The actual Rankine cycle differs from the ideal cycle by the reversibilities and the pressure drop in the boiler and the condenser. You'd have irreversibility in the pump and the turbine due to frictional and heat losses, and you'd have pressure drop in the boiler and the condenser due to phase changes. So the actual cycle differs from the ideal cycle by the dotted lines shown in the diagram. Now we're interested to find out the efficiency of the Rankine cycle. To find that out, we must know the individual components, um, enthalpy change or the energy change throughout the system. Now, the heat addition to the boiler is equal to the change in enthalpy of the fluid or the change in enthalpy of the working fluid throughout the boiler. So the change in enthalpy of the working fluid of the boiler can be found out by the enthalpy at the exit of the boiler minus the enthalpy at the exit of the pump. The work done by the pump can be found out by the change in enthalpy of the working fluid between the exit of the pump and the entry to the pump. Similarly, the work done in the turbine can be found out by the change in enthalpy of the working fluid from the exit of the turbine to entry of the turbine or the exit of the boiler. The heat rejection of the condenser can be found out by the change in enthalpy of the working fluid from turbine exit to pump entrance. Now the efficiency of the cycle can be found by the ratio of the net work done by the system, which is basically the turbine work plus the pump work divided by addition of heat, or it is equal to 1 minus heat out by heat divided by heat in. That is all from Rankine cycle today's lecture. If you have any questions, feel free to ask me during the class.